My pleasure to introduce Avy Soffer from Rutgers, and he's going to talk on from scattering to local decay, the case of time-dependent potentials and nonlinear equations. So please.
Thank you. So first I would like to thank the organizers for the opportunity to give this talk. And yeah, so I'm going to describe an approach to scattering theory which I worked on for the last 7 or 8 years or so with quite few people. And so you can see here the names. So Baoping Liu was the first one I worked with. He's from, at that time was assistant professor at Peking University. And after that, most of the work was done with Xiaoxi Wu, which is my former student, as a student, and Gavin Stewart and Yorgos Mavrogiannis, they were postdocs, former postdocs. Okay, so what I'm going to talk is about an approach to scattering theory and some consequences of this approach. And first of all, let me remind you what is scattering theory, at least in my view. So in scattering theory, we have two meta-theorems that we want to prove about any physical system. One meta-theorem says that if you wait long enough, then the complicated system will break into subsystems which are moving independently of each other. And each subsystem has its own effective dynamics. Right? So for example, if you have two particles interacting with each other, if you wait long enough, either they stay together and move with a constant speed, or they separate and each one of them will move with a constant speed away from each other. And the second meta-theorem is much more remarkable. It says that when you have a process if you look at a system, complicated system, and you look at all the pieces that come out later at infinity, if you know all of this, if you know all of them, you actually can use this to know everything about the original system. This sounds like something incredible, right? You can have a system which is super complicated. You look at it, you see nothing because let's say it is made of 10 to the 20 particles. But if you wait long enough, it breaks into pieces. You measure all the pieces aware. And from this kind of measurements, you can tell everything about the system. So these two theorems are, one of them is scattering theory, and the other is inverse scattering theory. Who was the first one who realized that? Da Vinci. Here is what he said. This is translated from Italian, but there are many translations, and each one of them says something else. But this is more or less the idea, that for some reason at his time, they thought that there is no vacuum, that if there is light moving, it must be vibrations of the air, right? So he said that the air between the bodies is full of intersections which are formed by the radiating images of these bodies. And this basically his way of understanding how he can see the Mona Lisa, for example. Right? Now, the thing is, if you look at it, there is something incredible in this piece of information. He says that we know, let's say that it was acoustic experiment, not with light. Let's say, then we know that acoustic waves move in air. But what he says is that not only the sounds is relevant to solving the inverse problem, but also the flow. In other words, the motion of the fluid itself, or the gas itself, is also containing information. This, I don't know how it is done. Okay, next is, I just summarized this. So I want to talk about a method of doing scattering theory which works also for time-dependent potentials and for nonlinear equations. So these are open systems. In other words, there is someone checking the system like that. Now, the physicists don't think that there is a difference whether you are shaking the target or not. So, for example, if you ask the Da Vinci tomorrow, if you ask, suppose Mona Lisa is dancing, is it still true? You say, yes, it's the same. What does it matter? Right? However, mathematically, there are no such results. There are no results which say that you can actually solve the scattering problem for a time-dependent potential and get the same kind of behavior, the same kind of two meta-theorems which I mentioned before. So the question is how to prove such thing. If you look at what people did, let's say in quantum mechanics or in other fields, you will see that basically always the target system is time independent. In other words, there's no forces from the outside, and special cases are always perturbative. There is a adiabatic theorem, there is a short pulse theorem, there is things like that. But there is no general theory that works for time-dependent potentials, and also no general theory for nonlinear equations, except for the thing that I will describe, which were done in the last 20 years or so. Okay, I don't have time to tell you all the history until today. I will just mention a few names. Sommerfeld, who introduced already a long time ago the notion of radiation condition. Then there was the great work of Rutherford in 1911, in which he was the first one to do scattering theory with particles, not just with waves, or electromagnetic waves or so, or sound waves, as people did before. And then until 77, these were basically the methods. So then Fadeev did his great work in the 63, solved the three-body quantum system. And this was using resolvent methods. And so in the process, he derived what is called now Fadeev equations, which play a fundamental role in physics today because it is what people use in people use it in many fields, but in particular, it was used from day one in nuclear physics. And in 78, Volker Enz, following some ideas which are from previous years, which in fact by Ruel and Haag, which were also for quantum field theory, he introduced a completely new approach to scattering theory. It's a time-dependent way. You forget about resolvents, you forget about generalized eigenfunctions, and so on, and you go and you look directly at the behavior of the solution in space-time. And you also do it by microlocalization. So you look at different parts of space, depending on what is the velocities and what are the directions in space. So this was basically started a new modern version of scattering theory. Here is a quick review of what was done. So in the case of minus Laplacian on a manifold plus a localized potential, this is what we call two-body problem. This started around 1920 or maybe even 10. Until today, it is still an active field. Fadeev did in 1963 time-independent methods. After that was Enz, and who did two- and three-body scattering by other methods, which is more general. And then there is a preprint of Moore and Siegel, which I know of, but nobody else, which does the three-body problem in a complete form. And then the n-body problem for all n was done by Siegel and me. We announced the result in 85. Graf in 1990 did a shorter and simpler proof of the n-body problem. And after that, there were many, many works. Quantum field theory, there are also some works. What about nonlinear equations? Nonlinear equations, it's a completely different ballgame. You cannot do spectral theory to attack a nonlinear equation because the interaction is time dependent, and so there is no Hamiltonian that you can use which is not time dependent. So the first work which were done in this direction, which are for all times, were for problems of the type in which you take an exact solution of the equation. You take an exact solution of this equation, like a soliton or a vortex or something like that, or a nonlinear bound states. You make a small perturbation, and you want to prove that as t goes to infinity, the solution breaks into two parts, a nearby soliton plus a free wave. And so the first time that a method was introduced to do such thing was in 88 by Weinstein and me. And then Galina Perlman we did it for minus Laplacian plus V plus nonlinear term. And our soliton was just a bound state sitting on the potential. Galina Perlman did it with solitons which are moving, and together with her advisor, Buslaev. Okay, then after that, it's uncountably many papers were written in this direction. I cannot count them all, but let me summarize some things about that. For the nonlinear Klein-Gordon equation, in one dimension, there is an exact solution, which is the kink. And the kink plus small perturbation, I thought, and other people thought, it is a nice new problem to do, which is in the same direction. It turns out that it is an awful problem, which nobody could do until very recently. More or less it was done by Luhrmann and Schlag, but it's not even that is not in complete generality. So this is the situation with, the one-dimensional kink. By the way, one-dimensional kink is a special case of a topological soliton. In higher dimension, it's a topological soliton. So asymptotic stability of this type for topological soliton is almost completely open at the moment. So we have methods, but we don't know how to implement them for this kind of problem. For the nonlinear wave equation, there is not much work, but if you put nonlinear wave equation on a lattice, which is like a system of masses and springs, then it is possible to do something about breather solutions and things like that on this kind of a lattice. There are works for other coherent structures. Coherent structures means exact solutions of the nonlinear equation, which is localized even though the equation is dispersive. So it's a localized solution of a dispersive equation. This is possible because the nonlinearity is focusing. So you have such solutions. So for example, vortices. And then there is general relativity. And in this, there was a parallel development in general relativity for this kind of problems. But it's slightly different. So here, the equation is quasi-linear. And the result here are of the type that the solution asymptotically is either exact solution, which is Minkowski, or exact solution, which is black hole or a rotating black hole, plus some small perturbation, which is vanishing on every compact set. So it is slightly different than the results in the other cases, and I'll explain that later on. Now, what can we do for a nonlinear equation, but not with small data, large data? How do you deal with large data? How do you deal with a general initial condition? It's not a small perturbation of a soliton, so you don't know what comes out. Because if you make a large perturbation of a coherent structure, it will break into many things. So what are the possibilities? So here is the possibilities, First of all, you get a free wave, which is just a part of the solution which spreads all the way to infinity. So part of the solution at infinity is a free wave. Another part is these solitons and coherent structures, because they are exact solutions, so you can get them as well. And what else? Well, what else is what is none of these? It's not of these two. So it is possible that there are weakly localized waves, which are not localized like solitons, but also not moving like free wave. They are moving slowly. They are spreading slowly. It's a priori, why not? The fact that everybody thinks that it is this and that doesn't mean that there is no this. And the fourth possibility is that none of the above, and so the solution is just big chaos. Right? So now we want to prove, for a given initial condition, which is large and arbitrary, we want to find what is the asymptotic state. That's the main goal of scattering theory. And the goal of the second theorem is, if I tell you what happens, tell me what is the nonlinearity. And in this direction, there is almost nothing. Almost nothing. Okay, so what are the known results on large data? So there is the the first one who did actually a series of non-trivial works is Terry Tao, and he looked at this equation, which is the nonlinear Schrödinger equation, and the power m is what is called intercritical. So it is below the critical and it is above the mass critical. And he said the following: assume the solution is uniformly bounded in H1. Not all solutions are uniformly bounded in H1. So we only talk about solutions which are uniformly bounded in H1. So if the solution is uniformly bounded in H1, we would like to find the asymptotic state. So we assume spherical symmetry. We assume dimension is larger or equal to 3. Then he proved what exactly you want to prove, namely that every such solution breaks into a free wave. You see, this is the dynamics of a free wave with some initial condition. And there is a leftover, which he could only prove that it is orthogonal to the free wave. It is not, and it is weakly localized. So he could not prove that it is localized. He could only prove that it is weakly localized. This is in the radial case. Okay? But he could prove something much more important. He actually proved that this weakly localized part is smooth. Even though the initial condition is in H1, the leftover, which stays here for all times, is a smooth function. Right? So, and this is true for arbitrary nonlinearity, as you can see. And this is something that he proved in a special case for the cubic NLS. And the reason for that we found out later, it's because you need the nonlinearity to be analytic in psi and psi star in order to be able to take infinitely many derivatives. Otherwise, you can only prove finite regularity. Okay, so this is during this period, 2004 to 2014, and then from 2014 to 23, Koenig and Merle, and later they joined by other people, worked on the nonlinear wave equation, which is energy critical. So this equation is special more than that because it is self-similar. It is invariant under scaling, right? So in particular, it has only one soliton solution. There's only one function that solves this equation if it is time independent. And then for this kind of equation, they actually gave a complete solution in some sense. It says that any solution which is in H1, which has finite energy, will break into a free wave and will break to a finitely many solitons which are scaled with some functions lambda j of t. And only one of them can be uniformly bounded. All the others are going to infinity or to 0. So all the other solitons are in fact the blowing up solutions. So that's and the leftover goes to 0 in the H1 dot. So that's what is known about the critical wave equation. There are no such results for general nonlinearity. Okay, so now I would like to describe quickly what we did in the last few years. So we looked at general dispersive equation. So H0 is not necessarily minus Laplacian. And the nonlinearity, as you can see, is pretty arbitrary. It is a function of psi, it's a function of x, function of t, it's fine. Okay? And then we said, okay, now assume this equation has a solution which is bounded in H1 uniformly in time. Then we prove the following, that if you have properly chosen operator, which is pseudo-differential operator of some sort, such that under the free flow, the interaction times psi in L2 is L1 function of time, right? Then psi of t will decompose into a free wave with respect to H0 plus a weakly localized part, and the difference will go to 0 in H1. So that's the result. But of course, I have to explain how to choose J. So if this interaction is furthermore localized in space, we have also other properties. For example, that the weakly localized part is going to be smooth in the sense that it is in HS for S, which depends only on the derivatives of how many derivatives of n you can take. And furthermore, we know that the weakly localized part breaks into something which is purely localized function plus something which is self-similar. So in other words, the weakly localized solutions are not arbitrary. They consist of a part which sits here and another part which is self-similar. So what is the main condition? The main condition that we need is that in order to satisfy the condition that I said before, the main condition that we need is that n times psi be in L1, uniformly in time. And the reason for that is that A does not have to be 1. It has to be close to 1, because this is really the main condition that we need. We need A to be such that this is true. And the reason for that you will see later, why this is enough. Okay. So what is this J that I constructed? So we are going to construct it like that. We are going to construct an operator JC out of this JF by conjugating it with the free flow. And when you conjugate it with the free flow, we put it in here. And then let's look what is going on here. We want to prove in scattering theory that the following limit exists, that you take the state at time t. This is the dynamics at time t. It can be nonlinear. So it acts on the initial condition. Then you take it backward under the free flow. And you want that the limit exists in the strong sense. This defines the molar wave operator, or the scattering wave operator. Okay, so we want to prove that this limit exists. That's all we have to do. So instead of proving this, we are going to put here a JC. This JC is an operator which micro-localizes in the region of phase space where the free flow lives. So if you project on this region, then you did nothing bad to this kind of limit. Because anyway, as t goes to infinity, we only care about the part which becomes free wave. So I project on the part which becomes free wave. In some weak sense, I'm going to project on this part. Okay, and then I can prove that this limit exists just with the condition that I mentioned before. And this is basically the idea of the proof. I will write later exactly how they construct this JC, and you will see that this follows from high school material. Here is why. X of t is x of 0 plus vt. That's high school, maybe even before. Therefore, x of t minus vt is x of 0. So therefore, it is of order 1. So what do? We project. We take a smooth characteristic function, and we project on x minus vt in absolute value over t to the alpha less than 1. So obviously, this projects on the part of the phase space where the solution is free. Well, who else can be there? Right? So that's the idea. What is v? I don't care what is v. For any h0, I can find a v. It is just the group velocity of the wave. So that's what you do. Now, how it is related to what I wrote before? Well, it is an identity that e to the minus I h0t f of x over t to the alpha less than 1 e to the I h0t is equal to this. This is straightforward calculation if you solve the free equation. This is a solution of the free equation. Right? So that's the idea. That's the starting point. And we did that for the Schrödinger equation, for Klein-Gordon equation, and for the wave equation so far. Okay. So we covered many cases in this way, and also problems which are not radially symmetric. So some of these results work also for non-radially symmetric case. For example, this problem, charge transfer Hamiltonian, is in fact a linear problem in which you have finitely many potentials which are localized and which are moving with constant speed. And you have a wave which is scattering of all of them. So that's one example. We did a three-body quasi-particle scattering. So it is three-body like before, except that instead of the Laplacian, it's a function, it's a more complicated function of the derivative. And this was open problem up until now, because the method which were developed for the n-body problem didn't work for the quasi-scattering. We also proved the Soliton resolution in 5 or more dimensions. This means that for NLS in 5 or more dimensions, for certain classes of nonlinearities and radial initial data, we proved in 5 or more dimensions that every solution is a free wave plus a localized part. There is no self-similar spreading part for this kind of equations. Okay, so now here is an example of a case for which it is covered. So you take a nonlinear term, which is a potential which depends on space and time, which is localized. We take another term, which is nonlinear, with G localized. And then we take another term, which is not localized unless it is radially symmetric, which is just general nonlinearity. Then for this kind of interactions, we have a solution, as we said, that the solution breaks into free wave plus a weakly localized part. So in 1 dimension and 2 dimension, this condition is very hard to prove, and you can only do it at the moment when the overall interaction is localized in space. So 1 and 2 dimensions are still open, let's say, for fully general nonlinear equation. And there are similar results for the nonlinear Klein-Gordon equation, nonlinear wave equation. And here I should say, I didn't put it here, but for all of these equations, you can add a localized metric perturbation. It doesn't make difference, because you can absorb the effect of localized metric perturbation just like you absorb the effect of these terms, as long as it is localized. Okay, now I'm going to talk about special case, which is linear and which is spectral theory. Pure spectral theory, except that it is fancy kind of spectral theory. So what is this problem? This problem is time-dependent potential. It is time-dependent potential with a time dependence which is quasi-periodic in time. So what does it mean? It means that it has two periods, omega 1 and omega 2, which are rationally independent. And so the potential term is V of x and t, such that t is a function of omega 1 t1 and omega 2 t2 and sum of a 2. So it is think of it this way. It is a sum of two periodic functions in time, one of them periodic with period omega 1, the other is periodic with period omega 2. So overall, this function is quasi-periodic. Quasi-periodic means it has finitely many periods. Okay? All right. So in this case, we can prove local decay and we can prove scattering. Now, why this problem is spectral and why you cannot do it by spectral method or by non-spectral method for so far? Because in the quasi-periodic case, you can reduce this problem using Floquet theory to a linear operator which is time independent and which has essentially nice spectrum. Even though it's not bounded below, it has essentially nice spectrum because it is basically the operator. So it's basically the operator k becomes I dt plus Laplacian minus v of x and t. So this is the operator now and it is on L2 where the time variable is between some, let's say, 0 to n pi for simplicity. That's the t variable cross Rn. So this is the Hilbert space. This is the operator. And the spectrum of this operator is easy to find out because the spectrum of this is all the integers up to a constant. And you take union with half line. And that's the spectrum. So it's very easy to know. This is a localized perturbation. So it is relatively compact. And so the spectrum, so this can only add all kinds of simple things, you know, like eigenvalues or whatever. So that's this problem. However, this is periodic. Why is it periodic? It's hopeless to do using standard methods because you have IDT1 plus I omega dt2 plus Laplacian minus v. And the spectrum of this is all the integers here plus minus all the integers times omega. And they are not rationally related. Therefore, the sum of these two, the spectrum of this is dense. Is dense over the whole real line. So since the spectrum of this is dense over the whole real line, this operator has a threshold almost everywhere. Okay? So since it has a threshold almost everywhere, all standard methods do not work in this case. Okay. All right. So what we can do, so you take this potential, which is a sum of periodic potentials, and so what we can prove under general conditions on the V is that you have this estimate, which is called local decay estimate. It says that if you take the solution at time t acting on an arbitrary function f after you project on the solutions which are supposed to be scattering. The fact that such an operator exists for this problem follows from the previous part that I discussed, namely that scattering theory holds. In particular, it says that you can construct this projection. And then what this estimate says is that locally the solution, if you take a scattering state, then locally the solution decays like a square integrable rate in L2. This is an L2 norm, locally. Eta has to be large enough. This is an absolutely crucial kind of estimate because in the standard approach to scattering theory, you first of all prove this and then prove scattering. Here we are going to do backward. We are going to prove scattering and then we are going to use scattering to prove that this estimate is true. Okay?
Is this, and you say the space dimension is bigger than, this is large. The space dimension is bigger than 8.
Oh, this is, now it's 5.
Oh, okay, that's better.
Okay, so now it is 5, but you need some conditions on the technical conditions which says that the projection on the bound set is localized. In other words, that the bound sets cannot be like 1 over R or something like that. So this is the condition. And then it goes all the way down to 5. 3 is very problematic. To go below 5 is very problematic because in order to do below 5, you see, in 5 dimensions, the Laplacian does not have zero energy resonance. In 3 dimensions, the Laplacian has zero energy resonance. Since it has zero energy resonance, there has to be an extra condition which removes the zero resonance once you add the potential. The Laplacian itself does not satisfy a good estimate because of the zero energy resonance. If there is a resonance at thresholds, the solution does not satisfy the standard estimates. So for example, the quasi-periodic case, you can have resonances at all the threshold points, and then you don't know what to do. So in 5 dimensions, you don't have resonances. Therefore, you don't need extra conditions. But if you want to go below 5 dimensions, you have to put extra conditions that avoid the presence of resonance, zero energy resonance at the origin. At the origin, in the case of the Laplacian, at thresholds in general. So if the threshold is 17, then you have to know that there is no generalized eigenfunction which sits there. For example, the function 1 is an eigenfunction, is a generalized eigenfunction of the Laplacian. But only in 1 or 2 dimensions it is relevant. So that's the problem with thresholds. Okay, so if someone knows how to use Moore estimate in order to prove decay estimates, it also doesn't work, because since the thresholds are everywhere, you cannot find an interval on which the Moore estimate holds. It's not possible. All right. So let me say some idea of the proof. And I will only explain it in the time-independent case and only for a caricature of the original, of the true problem. So what you do is you take the full solution and you write it as the free part, not very hard to guess what it is, plus an operator times plus some operator times the full solution. And then we claim that this operator C you can write as a sum of 2. One of them is small, but unfortunately the other one is not small. So this one is small and localized, but the other one is not small, so you have to prove that it satisfies local decay. So you have to prove that this quantity satisfies local decay. If you can prove that it satisfies local decay and this one is small, then by bootstrap you can close. All right. Now, first of all, in order to deal with the CR, because it is small, you just move this term to the left, you divide by it, and you get that you are left with basically controlling this part, which is the inverse of 1 minus CR times CM times this. And in order to do that, you use scattering theory. You use the fact that you know that both these wave operators exist. This one and its opposite, and exist and are complete. And now let's make an assumption which trivializes the situation. We assume that this original C is a trace class operator, and in particular rank 1. And if you assume that it is rank 1, then you can write it like that. And rank 1 does not mean that it is small. So you still have to work in order to deal with the fact that you have an operator there which is not small, right? So what do? You use the fact that you know that asymptotic completeness holds. What does it mean? It means that you know that these operators give you the full story. So in particular, the projection on the scattering states can be written as omega times omega star. And you use that to calculate Cm by breaking it into 2 parts. One part, you break the x here to x small, some number m, and then another part with x large. The part with x large is a small operator, so that's the CR part. And the part which is small, you have to prove that it satisfies local decay. And this you do by using the intertwining property of the molar wave operator. So this is one more thing that we learn from scattering theory. If you constructed this operator, you actually constructed the operator that diagonalizes the Hamiltonian. This operator diagonalizes, this is the transformation that diagonalizes the Hamiltonian. This is true in the time-independent case. But in the time-dependent case, you can still use it in some modified way. Okay. So then we put this kind of identity, omega omega star. We move omega star back and forth, and what happens is that you have at some point you have omega star hitting the e to the minus ith, and when you move the omega star to the other side, it becomes e to the minus ith 0, and therefore everything is reduced to estimate with respect to the free flow. So this is the caricature of the original argument. It's much more complicated when it is done for the quasi-periodic problem, but this is essentially the idea why scattering theory is sufficient to prove local decay. So you can see here some more details. So you see, at some point you have omega star acting on e to the minus ith, but when you move it to the other side, it becomes e to the minus ith 0. So therefore, localization in x times the free flow times a function in L2 is in L2 in time. Okay? So that's the idea of the proof. This method was used also to prove the solitary resolution. In other words, that in 5 or more dimensions, nonlinear Schrodinger equation with radial initial data, the solution breaks into 3 parts plus a localized part. In other words, there is no self-similar tails to the solution if you take at least in 5 dimensions for nonlinear Schrodinger equation. Okay, so now this is something which is not yet posted, but it is possible to generalize this method to the case of long-range potentials. So in other words, if the potential V decays in x like 1 over x to the mu, where mu is 1 or less, like Coulomb scattering, for example, then it is possible to use this method, but of course there are modifications. For example, the free flow has to be replaced by modified free flow. And this modified free flow is time dependent. So it adds some complications to the story. So nevertheless, the question arises of what can you say about the weakly localized part? So it turns out that the weakly localized part can spread much faster than 1/2. We prove that it spreads no more than half in the case of short-range potentials or short-range nonlinearities. But for long-range, it can spread faster. So if you know the behavior of Coulomb's scattering, you know that there is a trajectory for Coulomb scattering or gravity, which is not a free wave, which is not a free particle moving ballistically, and it is not an elliptic trajectory, but it is a parabolic one. It goes like x like t to the 2/3. There's one such solution. And it turns out that this is exactly what happens here. The weakly localized part can spread, our estimates say that it can spread just like t to the 2/3 in the case of Coulomb. There is a general formula for how it can spread, depending on mu. So here are some more details. You see the free flow now is not free anymore. So it is, what you do is you take the original potential and you replace x by the velocity times t. That sounds obvious, but this was the PhD thesis of Dollard in 1964. This idea that this is how you can find asymptotic behavior for Coulomb for long-range scattering, and then you can prove scattering. All right. So that's the theorem that we have so far. We have to assume that mu is larger than half. Then the asymptotic behavior is good. However, because the potential is time dependent, we don't know if the solution is global even. So we have to assume that if we assume that the solution is global, in other words, it's uniformly bounded in H1, then you can get more estimates. And for example, that the remainder term is localized in the sense that it cannot spread. And as I said, it cannot spread too much. But for this, we have to know that the solution is uniformly bounded in H1. So this is the spreading rate, the maximum spreading rate of the solution in the long-range case. In the short-range case, it is 1/2. But in the long-range case, it is 2 over 2 plus mu when mu is larger than half. Right? So you see from here that if mu is equal to 1, which is the Coulomb case, then you get t to the 2/3.
And is that kind of behavior generic, or is that non-generic?
For the Coulomb problem, or gravity, it's non-generic. You never see it. Nobody can see it. And anyway, this is quantum problem, not classical. But the solution, this spreading is the spread of the solution around the classical trajectory. You see, it's a quantum system. So the wave function is spread. But you ask yourself how much it is spread around the classical trajectory. And in the long-range case, it is very bad, because it can spread like t to the 2/3 in the Coulomb case. So you cannot really do estimates under the assumption that the solution asymptotically is very well localized near x equal to vt because of this. So it's a purely quantum thing. It's not, okay, this is just a trick which was used for this work, which is to break the long-range case into two parts, one long-range and one short-range, or if you want, one internal, one external. Because if you break the potential, you see, this is something that you have to do because the potential is time-dependent. So you first of all project on the region where x over t to the beta larger than 1, and you call it v external, and then you do v minus v external. V minus v external is nice because it is projection on x less than t to the alpha, and this region is like short-range potential. The potential is dead after a certain distance, which is equal to t to the alpha. This one is also nice because you don't have to prove local decay in order to deal with it, because you have already projection on x larger than t to the beta. And if beta is not too small, then it kills everything near the origin. So you see, this one, you don't need local decay, so you can deal with time-dependent potential. This one is short range. So that's a good to know that it is possible to deal with long range in this way. Low dimension. So in low dimension, we cannot do, as I said before, a purely nonlinear problem. However, if you take repulsive nonlinearity, in other words, defocusing, and you add a general localized potential which may be time dependent, then we can do quite few things, as you can see here. For example, we have a bound on the spreading, and the fact that in this case, depending on the parameters of the problem, x does not grow faster than t to the 1/2. And in some cases, it cannot grow even like t to the 1/3. You see, it's even better than the general case. The reason is that the nonlinear term is repulsive, so you can use that. This is the end of part 1. Okay. Part 2 I will not show because it is details of the proof and so on and so forth. But I will try to tell you about part 3, which is a list of open problems. And I will tell you only one of them in spectral theory, because this is the most important problem. This is the most important problem from all the list. By the way, you can see part 2 and part 3 also in my recent work on recent review paper, which is called The New Paradigm for Scattering Theory. You can find there all of these things. But I want to tell you about the problem, which is spectral theory, and which is fundamental because of what it implies. So the problem that we need to solve is the following. We have the Floquet operator, periodic or quasi-periodic. In fact, it doesn't matter now. This is periodic, and this is on L2 of the interval cross Rn. What we need to prove is that if n is larger or equal to 2, to characterize those V, and I tell you where they are coming from, such to prove that if n is larger than 2, they cannot have embedded eigenvalues. Sounds simple, almost like Riemann hypothesis, right? It's just you have a simple manifold. You have a simple manifold, and all you have to do is to prove that this does not have. Now, I want to tell you why it is very important, right? It's more important that you know why. It gives you motivation to do it tomorrow. If you can prove that for n, by the way, for n equal 1, it's not true. But for n larger or equal to 2, there is a conjecture by physicists. The conjecture says that nonlinear Schrödinger equation, let's say, cannot be completely integrable if it is in 2 or more dimensions. In other words, you cannot find a nonlinear equation, which is Schrödinger equation, let's say, minus Laplacian plus something, such that you can it is completely integrable. In other words, there is no Lie algebra of infinitely many symmetries of this equation. So this is a statement about nature. It says that nature cannot write down an equation which is completely integrable in 2 or more dimensions. So half of the physicists say that the conjecture is true because of these obvious reasons. The other half of the physicists say it is not true because I can do it by other methods. So we don't know the result. But the people I talk to think that it's not possible to do it's not possible to write completely integrable system in 2 or more dimensions. So that's the issue. So if you can prove. Now, what this has to do with embedded eigenvalues? Here is what it has to do. One way of studying this question of whether there are completely integrable systems in 2 or more dimensions is to find an equation that has solutions which are solitons or breathers. Breather is a periodic solution, so it lives here. If the nonlinear equation has a breather solution, which is time periodic, you linearize the equation around the breather, and you immediately conclude that the breather corresponds to an embedded eigenvalue of this operator. So this is the relationship. If there is a breather, there has to be an embedded eigenvalue. Why it has to be embedded eigenvalue? Because the spectrum of this operator covers the whole line. So if there is a breather, so the claim is there are no breathers in 2 or more dimensions. In fact, there is a similar conjecture in 1 dimension which says that for the nonlinear Klein-Gordon equation, there is only one nonlinearity on Earth for which there is breather. This is another conjecture which was proved partially over the last 60 years or so, 65, 70 years, in all kinds of special cases and situations. But it's also open that in 1 dimension, the only solution of the Klein-Gordon equation in 1 dimension, which is a breather, is one particular nonlinearity and nothing else. So this corresponds to complete integrability. So now, what do we know about the spectrum of this operator?
Sorry, but what are the boundaries? You mentioned periodicity. I didn't understand what it means. What are the boundary conditions here on the interval I?
It's periodic function. So it is periodic function. So you can think of it, right, as a circle. Right? It's a circle, right? Yeah, it's a circle. So you have a circle. If it is quasi-periodic, it is donut, but it's a cylinder. That's what it is. So now, what do we know? What can spectral theory do? There is a general theorem. There is a general theorem. There are many general theorems, but the one that there are general theorem that says that if you have an embedded eigenvalue for a general self-adjoint operator, then it is unstable under small perturbation. Of course, there are conditions to the theorem, right? So what are the conditions? The condition is local decay. This is the best result. So if this is the continuous spectrum and there is an eigenvalue here, then the theorem says that if you have if you take this absolutely continuous spectrum in here and you prove local decay for initial condition sitting on this spectrum, which is absolutely continuous, then this eigenvalue is unstable. Under small perturbation, practically any small perturbation, it will get killed. It will not get killed only in a special case when the Fermi golden rule is not satisfied. This is something that number theorists use as well, though they discovered it independently of physicists. It goes back to the original work of Sarnak and Phillips. Sarnak and Phillips. Right. So, but I just proved local decay. Right. So I just show you that we can prove local decay. So the local decay that we proved, at least in high enough dimension, implies that all of these guys are unstable. Right? But the fact that they're unstable does not mean that they are not there. It means that this is non-generic. So what we can prove is that if you are in high enough dimension, then all these breathers are highly, they are unstable, they are non-generic, and so it's a miracle if you find an equation which satisfies this. That's why this problem is so difficult. Okay, let me stop here.
Any questions?
Is the weakly localized part of your wave, did you get it by a kind of something explicit, or is it a compact sum?
Yes. We have a paper in which we actually showed that if you work in 3 or more dimensions, we can write down explicitly potentials v of x and t such that they decay like 1 over x squared at infinity, and such that the solution has weakly localized solution which spreads like t to the epsilon for every epsilon up to 1/2. And we prove that these solutions are in fact stable. So they are not blowing up like the results on the soliton and whatever. These solutions are stable. So you make a small perturbation, they are still there. They are generic part of the asymptotic state of the system. So in other words, if you have a time-dependent potential, the standard picture of scattering theory is wrong. It's not just free wave and localized. There is also something which spreads.
And when you prove that they're present in your general theory, how do you do it?
We prove that if certain conditions are satisfied, and if the potential V is of a particular form, then there will be such solution. So it's not that there could be. There are if these conditions are satisfied. It's explicit construction. Okay. We don't know how to do it for purely nonlinear equation.
The X space is unbounded, so any conditions on V that you assume?
Yes, V is supposed to be the solution of the nonlinear equation. So we know that it is smooth, it is exponentially decaying. Beautiful.
Yes.
You were kind of teasing at the beginning about connections to quasi-linear models, stability.
Yes, okay, I forgot to mention that. Here is the thing. You should not be angry at me, but I have to say it. All the results which people proved on stability of black hole and Minkowski are stability, but not asymptotic stability. In what sense? In the sense that the remainder term, in the case of soliton dynamics, the remainder term, we know what is the equation it is satisfying. It's satisfying the free Schrödinger equation, the free Klein-Gordon equation, the free wave equation. In the case of general relativity, it was not shown that the remainder term is a gravitational wave. Yeah, so it is not shown. Even in the Minkowski case, it is not shown. Maybe it follows.
Obviously, you're saying it's not showing the form.
It's not shown, yes. Maybe it is. Maybe you can prove it tomorrow because it follows. But it was not shown that the remainder term, which is not Minkowski spacetime, is a solution of the Einstein equation, which corresponds to gravitational wave. That's the part which is missing in order to say asymptotic. You see, what is scattering theory says? Scattering theory says that if you see the wave at infinity, you know everything about the system. But how do you know from the results on stability of black hole, that what you are going to see at infinity is gravitational wave. Right? The only thing you know is that it is moving. The only thing you know is that it is spreading. But you don't know that when it is spreading, it becomes gravitational wave. You know, gravitational wave is a complicated solution. There are not many solutions like that. So that's, I think, is something which I don't quite understand.
Any other questions? Actually, for this, I was asking Schlag when he was giving a talk about the proving non-existence of embedded eigenvalue for some other problem.
Yes.
And he sent me a paper that has just appeared, has been accepted at Invenzione, where they use computer-assisted proofs to prove it's like 75 pages.
I know
Is
this.
this related? Can that approach apply or include this case?
Actually, it's not related. This is a absence of embedded eigenvalues for the nonlinear Schrödinger equation and cubic nonlinearity, something like that. So you see that when you linearize around a solution of the nonlinear equation, bad things happen. And the bad thing that happen is that the linear operator, besides the eigenvalue which corresponds to your soliton, there are all kinds of spurious eigenvalues which appears all over the space. And the reason that there are all these eigenvalues which appear all over the space is because these solitons can vibrate. Or it can do this. And all of these vibrations are manifested by the appearance of eigenvalues in all kinds. They are not real eigenvalues, they appear in the complex plane. So in fact, they are resonances. But all these resonances, some of them are eigenvalues, but the resonances correspond to finite lifetime vibrations of the soliton. And some of them, which are real valued, corresponds to the fact that the soliton can be excited. So it doesn't have to be, it doesn't have to be like that. It could be like that. So there are many, many, many eigenvalues. And when people fix attention to one particular equation, like nonlinear Schrödinger equation with cubic nonlinearity in 3 dimensions, in 3 dimensions it's not completely integrable. So then there was a hard work to prove that there are no this kind of spurious eigenvalues. It's called spurious eigenvalues. It's not these ones. Yeah, this is easier, I don't know.
Okay, because
Yeah.
it's hard. Okay, I guess it's raining, so we can still ask questions.
Don't swim in it.
Yeah, exactly.
Thank you again, and